Am I audible and my screen visible? Okay, fine. Thank you very much. So, good morning. Now, anyway, others may join later. So, but we'll start this today's session. Now, in today's session, we will talk about the minimum cost spanning trees. Now, this is also a topic which comes under greedy method, or greedy approach, or greedy strategy. Now, we have seen zero one knapsack, we have seen job sequencing with deadlines, and this is the other topic which comes under the greedy method, or we solve the minimum cost spanning tree problem with using greedy method or greedy approach. Now, graphs. Usually, we create a minimum spanning tree from a graph actually. So, graph is nothing but they have several applications. For example, graph can represent airports, and the edges may represent the flight paths, and each cost may have a weight, and the weight may represent the flying time, or the weight may represent um, the cost of the ticket, or several other cost metrics can be applied here. Now the question is, uh, what is the shortest path from one place to the other? Though that this question generally is the uh, comes into mind of everyone. The shortest path problems and all are solved. There is a different technique to solve all those things. But what we try to do here in this minimum cost spanning tree is that we take a graph and create a tree from that graph, and that tree, all the edges combined together, should have the minimum cost. So let us consider we have a graph G where V represent vertices and E represents the set of edges. Now, graph you can have any edge. A graph may have any number of edges, doesn't matter. But this is a sample graph here. Take it. Now, for this graph, a spanning tree. Spanning tree is defined as T, a set of vertices V, and edges E dash. Now, when we say set of vertices V, that means all the vertices of a graph should be there in spanning tree, in the tree. And this T is a spanning tree if and only if T is a tree. When we say T is a tree, that means there should not be any cycle. There should not be any cycles. In this case, if you see this graph, we have vertices 1, 2, 3, and 4. Now, if you look at the edges, there is a cycle from 1 to 3, 3 to 2, 2 to 1. But tree cannot have a cycle. So that is the point we need to remember. And here in graph we have E, but in the tree, spanning tree, we say we have E dash. Now this E dash is nothing but different from E. E dash is actually a subset of E. So let us consider this, the figure which is there on the left side. Now this is a spanning tree because there is no cycles first of all, and all the vertices are there in are same as what we have in the graph, and we have certain edges. So vertices are same, and then the edges E dash is 1 to 2, 1 to 3, and 2 to 4. This E dash is a subset of E. Now we cannot have a new edge in the spanning tree. Whatever edge is there in the graph, that same edge will be used, but it will be a subset. So remember one more thing: there is no new edge we can have, we can only use edges which are there already, which are already there in the graph. Now, this of informal definition leads to some of the properties of the spanning tree. The first property is all the vertices, as I said, all the vertices of graph G are in spanning tree T. So V, set of vertices V in graph and set of vertices V in the spanning tree will be same. Then spanning tree T should be connected. Remember, we may have all the vertices of graph in a spanning tree, but all those vertices should be connected. Should be connected. That is another important step there. Otherwise, it will not be a tree. Then, the third property is that the spanning tree is acyclic. That is, there should not be any cycles in the spanning tree. Now, remember, right? We are just talking about spanning trees right now. We will discuss about spanning minimum cost spanning trees later. So spanning trees has three properties. That is, all the vertices in the graph will be there in spanning tree. Spanning tree should be connected, and spanning tree should be acyclic. There should not be any cycles. Now, spanning tree is sometimes also known as minimal subgraph. Minimal subgraph. So actually, spanning tree is nothing but a subgraph of a graph G. Now, why we say minimal subgraph? Because we can use minimum number of edges to create a spanning tree of a graph G. Then it's not that we can only have one spanning tree. There can be any number of spanning trees. For example, let us look at another set of edges which we use to create a spanning tree. Number of vertices will be same, but let us say we have an edge between 1 to 3, 3 to 2, and 3 to 4. These edges are already there in the graph. So this also becomes one of the spanning tree. Then again, we may have an edge between 1 to 2, 2 to 4, and 3 to 4. These set of edges are also there in the graph. So they can. So we can have several spanning trees. In this case, we have only generated 3 spanning trees, but they can be several spanning trees. Now, usually what happens is, if there are n number of nodes or vertices, then in the spanning tree, I'm talking about spanning tree, for in the spanning tree, if there are n number of vertices, then there will be minimum n minus 1 edges. There will be minimum n minus 1 edges, and this property is very useful. We say why we say n minus 1 edges, because if all the vertices has to be connected, if the spanning tree has to be connected, then we need, for n vertices, we need n minus 1 edges. We need n minus 1 edges. So this is one of the property. So in this case, all the graphs has all the spanning trees has 4 vertices. So we have edges as 3 as the edges there. Now, the edges of the graph are usually associated or has some weights. Now, these weights, maybe like example we have talked about for an airports, the flight paths are the edges, and they may be the weights of those edges. The cost of the edges might be airfare or flying time or distance. So basically, edges will have some weight. So here, what we are talking about is we have talking about a graph, a weighted graph, and weighted undirected graph. There is no orientation for edges. It's an undirected graph, weighted undirected graph, which is connected. So we are talking about weighted connected undirected graph. So once we have the weights on the edges or cost on the edges, the cost of the spanning tree, each spanning tree, cost of the spanning tree will be sum of the cost of the edges. Sum of cost of the edges, and edge should belong to the spanning tree. Now, not the cost of the edges of the graph. For the spanning tree, the cost of the spanning tree is the sum of cost of all the edges which belongs to the spanning tree. So that's why C comma W, if this is an edge, sorry, it should not be C, it's actually V comma W over here. So V comma W, the cost of V comma W, summation of cost of V comma W is the cost of the spanning tree, where V comma W is nothing but belongs to E dash, not E, E dash. E dash is nothing but set of edges. So in this case, we have 3 plus 2 plus 4, which is 9. The second spanning tree has got 3 plus 6 plus 1, which is 10. And the fourth spanning tree has got 2 plus 1 plus 4, which is 7. So cost of the spanning tree is the sum of cost of their edges. Now our problem is to find the minimum cost spanning tree. Now these are three different spanning trees for this graph, but they may be several other spanning trees. So just by looking at these trees, we cannot say that this is cost is 7, so this is the minimum cost spanning tree. We cannot say, because there may be other spanning trees also which may have, less than this cost. So we can't say that. So anyway, what minimum cost spanning tree is, this summation, the cost of the spanning tree, summation of cost should be minimized. So if the cost of the spanning tree is minimum, then we say it's a minimum cost spanning tree. So here the problem is minimization problem. The earlier problems of the greedy method, that is job sequencing with deadlines and and the knapsack problem, what we have seen was the maximization problems, where we were talking about how to maximize the profit earned. But here in this case, it is a minimization problem. That is, we have to find the minimum cost of the spanning tree. Now let us move further. So what will be the greedy approach? The greedy approach of building a spanning tree, which will be a minimum cost spanning tree, or constructing a minimum cost spanning tree, is to construct the tree edge by edge, taking one edge at a time. And the next edge which we try to choose should minimize the sum, should minimize the increase in the sum of the cost. So this is the greedy approach. Now there are two approaches here which we can use. One algorithm is known as Prim's algorithm, and the other algorithm is known as Kruskal's algorithm. So to find a minimum cost spanning tree, we can use either Prim's algorithm or Kruskal's algorithm. Both uses greedy approach or greedy method, greedy strategy, but there is a difference in both the approaches. So let us look at what the Prim's algorithm is. What Prim's algorithm says is we start by selecting a random vertex, on an arbitrary vertex from the graph. Now it's actually generally the vertex which has a least cost. Then there is a set A we maintain, which stores the edges of the graph which forms the tree. And at each stage, what we do is we select the next minimum cost edge such that the tree which grows is a connected tree. So we select an edge u comma v which is not already there in the set A, that means which is not already there in the tree, and we merge the set u comma v, we merge the edge u comma v in the existing set A of the edges of the tree, spanning tree. Now when we merge it, it should also form a tree. What this means is the edge, whatever we are going to select, next minimum cost edge, whatever we are going to select, that should not form a cycle again. It should be a tree. So this process of selecting the next minimum cost edge and all continues till we explore all the vertices of the graph, and all the vertices of the graph is present in the tree. That is what was the one of the property of spanning tree. That is, all the vertices of graph will be there in the spanning tree, and that too connected. So, I mean, an informal algorithm would be, a Prim's algorithm would be, to repeat these steps of finding the minimum edge and minimum that to connecting A. So once we select an edge, when we select a vertex, endpoints, two vertices of the edge, the next edge which we select should be minimum, and that should be connecting to A, connecting to the tree. So tree should be, as tree grows, it grows in a connected manner. And then union the edge which we have selected. This repeat until all the vertices are there in the tree or in a set of edges. Now let us practically look at how this Prim's algorithm works. Let us consider the graph on our right hand side. This is the graph with 7 vertices and its respective edges, and each edge has got a cost. Now a spanning tree T, we're going to construct a spanning tree using Prim's method. So spanning tree T, initially the set A, which is a set which contains the edges of the spanning tree, is null. Initially it's null. Then let us consider we are selecting vertex A. Once we select vertex A, what is the minimum cost edge actually from the graph? It's 10. And 10 is with vertex A. So let us assume that we select vertex A. Vertex 1. And 10 is the minimum cost edge. Now this vertex 1, which has minimum cost edge 10, connects vertex 6. So what we do is we select this edge and the vertices with it, and that edge is placed in the spanning tree, and we union the edge u comma v. U comma v, that is 1 comma 6 in set A. So set A now will be containing an edge 1 comma 6 with on vertex 1 to vertex 6. Then what we need to do is we need to select next minimum edge, not among all edges. The next minimum edge is 12, but next minimum edge not among all the edges. Next minimum edge connecting A. What is A? 1 comma 6. So connecting 1 comma 6, and which is not in A. So which edge is connecting 1 comma 6? Connecting 1 comma 6 means connecting 1. There is an edge between 1 to 2 which connects 1, and there is an edge between 6 to 5 which connects 6. And remember, 1 comma 2 is an edge where 2 is not in A. Vertex 2 is not in the set A, and vertex 5 is also not in set A. And who is minimum among these two? 28 or 25? 25 is minimum. So we select the edge, minimum edge u comma v. Here u is a vertex 6 and v is vertex 5 to a vertex not in A, connecting, and not in A. 5 is not in A. So we select this edge and create a spanning tree, and then put 6 comma 5 in the set A. Merge it, union of that. Now next, what do we have to do? Find minimum edge u comma v connecting A, that is connecting 1, connecting vertex 1, vertex 6 and vertex 5. What all are the vertices connecting 1, 6 and 5? What all edges are connecting 1, 6 and 5 vertices? There is an edge 1 to 2 which is 28. There is an edge 5 to 7 which is 24, and then there is an edge 5 to 4 which is 22. So this edge 22 connecting vertex 5 and vertex 4 is minimum. So we select that edge and grow the spanning tree. That edge is placed in the set A of edges. Again, we have to select an edge connecting A, that is connecting vertex 1, vertex 6, vertex 5 and vertex 4. What are those edges? We have edge 24 connecting 5 and 7, edge 4 connecting edge 18 connecting 4 and 7, edge 12 connecting 4 and 3, and edge 28 connecting 1 and 2. What? Which edge is minimum among this? Edge connecting 4 and 3. So we put that edge in the spanning tree and then add that edge to set A. Next, we have to consider now minimum edge connecting A, that is connecting vertex 1, vertex 6, vertex 5, vertex 4 and vertex 6. So there is an edge 28 connecting 1 and 2. There is an edge 16 connecting 2 and 3. Edge 24 connecting 5 and 7 and edge 18 connecting 7 and 4. Which is minimum? 16. Edge with cost 16 is minimum. So we select that edge, put it in the spanning tree and union it with the set A. Then what is the next? Now next minimum edge connecting A is from 1, 6, 5, 4, 3 and 2. So these are the edges, and among these edges 28, 14, 24 and 18 we have an edge 14 which is minimum. So we select that edge and put it in the spanning tree, and that edge is added to A, set A. Now should we proceed further? No. If we proceed further, we will be creating a cycle. So therefore, we will not proceed further. Why? Because all the vertices are in A. You see the set A, all 7 vertices are there in set A. And the Prim's algorithm terminates, and we have the minimum cost spanning tree. Definitely, Prim's algorithm, using this procedure, we will get a minimum cost spanning tree. Now what we have to see is, we have to select, remember we need to find the minimum edge connecting A to a vertex not in A. Now if we consider, let's say next minimum edge would be 18 because we are left with 28, 24 and 18. Next minimum edge will be 18. Assume all vertices not over, assume that. Now 18 is an edge between vertex 4 and 7. So can I add this vertex to 4 and 7? If I add, it will create a cycle. Then how am I protecting the spanning tree from having cycles? The statement is connecting A. Here, the statement in the algorithm, which says connecting A to a vertex not in A. This prevents us from creating a cycle. Why? Because if you select this edge from 4 to 7, now look at here. Both 4, vertex 4 is in set A as well as 7 is in set A. So when both the vertices or both the endpoints of an edge, both the vertices of an edge are in set A, then do not consider that edge, discard that edge. If you consider, it will create a cycle. So if both the vertices, endpoints of an edge are in the set A, which is a set of edges of the spanning tree, then discard that edge. So this is how Prim's algorithm works. Now let us look at the the cost of the Prims. That is, what will be the cost of this spanning tree created by Prims? Sum up all the edges, and here we get the cost as 99. Now let us try to look at the actual algorithm. What we have seen is a informal it's like a descriptive Prim's algorithm, but actual implementation is done using a pseudocode, and this is the Prim's algorithm. What we have is the Prim's algorithm takes 4 parameters, that is E, which is a set of edges, cost is nothing but it's a cost adjacency matrix where all the cost of edges are stored. N is the number of vertices, the third parameter, and T is an array, two-dimensional array, which contains two columns, only two columns. The first column, we store the vertex, the first vertex of the edge, and second column we store the destination vertex of the edge, the second another vertex of the edge. And this T array, two-dimensional array T, which has only two columns, actually stores all the edges of the spanning tree. That is nothing but this T array is the set A, which we have seen in the previous example, how we solved it. The very first statement, let K and L be an edge of the minimum cost in G, that is in E. That is, among all the edges, select the edge with the minimum cost. That is arbitrary, we are trying to select a vertex and with the minimum cost edge. So let's say K is vertex 1 and L is vertex 6. Now we will have a variable minimum cost, which is the cost of K comma L, because that's the only edge right now between vertex 1 and vertex 6. So we assign it to minimum cost. Then T, I said it's an array, two-dimensional array, where first column is the source vertex, that is K, and the second column will have L. This is not 1, this is L actually, L. So L is vertex 6. So T is the array which will be storing the edges, and right now we have edge from vertex 1 to vertex 6. So vertex 1 to vertex 6. Then we use a for loop, this for loop from line 5 till line 9. This for loop is used to actually assign the values to another array known as near. So we will be maintaining an array near. The size of this array will be number of vertices, and the index of the array will represent the vertex, actual vertex. The near array actually will be having value 0 if the vertices are already there in the spanning tree. Else it will have some other value. Now, if you just try to solve these statements from line 5 to line 9, we get near of 2 as 1, near of 7 as 1, near of 3 as 1, because if there is no edge between 1 to 7, or there is no edge between 1 to 6, 1 to 3 actually, no direct edge I'm talking about, then it's taken as infinity. So cost of infinity less than infinity will be, it's false actually. So I value will be assigned K, which is in this case 1. So a near of 2, near of 7, near of 3, and near of 4 will be assigned 1 if you solve this. And near of 5 will be assigned 6. That means near of 5 means near of this vertex 5. Which vertex is near to this vertex 5? Vertex 6. Now obviously vertex 7 is also near, vertex 4 is also near, but near at the first instance is near to the vertex of the spanning tree. So right now we only have vertex 1 and 6 in the spanning tree. So the vertex 5 nearest is 6. So if we include this, we will be growing the spanning tree. Then even in case of near of 2 is assigned 1, because this is because, though obviously 7 is also near to 2, 3 is also near to 2, but at this stage spanning tree only has vertex 1 and vertex 6. So near vertex of 2 is vertex 1 and near vertex of 5 is vertex 6. This is because to grow the spanning tree, to have the spanning tree, grow the spanning tree in a connected manner, in a connected way. Then as I told you, the near index, the vertices which are there in the near array, which are there in the spanning tree, their near value will be 0. So since K and L are the two vertices which are right now already been selected, K and L, and which will be there in the spanning tree, so we assign 0. So that's why 1, vertex 1 will be, the near will be 0, vertex in near will be 0. Then from line 11 till line 19, what we do is we iterate, that is each stage, what I said. At each stage, and this for loop runs from 2 because first edge we have already computed and put it in the spanning tree. And for n vertices, I told you there will be n minus 1 edges. So that is why for loop will run from 2 to n minus 1. And at each stage, at each iteration, we select a vertex which is not in A. That is, near of j should not be 0. If it is 0, some vertex j, we select some vertex j, which is an index. I mean, index is representing the vertices actually in this algorithm. So near of j, near of that vertex should not be 0. That means if it is 0, that means that vertex is in the spanning tree. If it is not 0, that means it's not in spanning tree. And cost of that vertex with the near j is minimum. So if you look at this first step, cost of, let us say 2. So cost, let's select j as 2. Cost of 2 comma near of 2 is 1. So 2 comma 1 is 28. And cost of j is 5. Let's say j is 5. Let j be the index such that this is not 0. So j is 5. And cost of 5 comma near of 5 is 6. So cost of 5 comma 6 is 25, which is minimum 25. So that is why we are selecting this edge. Now this edge j over here will be 5. Now you can have for I equal to, so j can be anything else, or j can also be 4. But 4 of 1, j of 4 is not null, then 1 comma 4 will be infinity. It's not minimum, it will be infinity. So at this stage, when this j is selected, it is selected such that the vertices are near. That's what it picks up. The minimum, when we say cos j comma near of j is minimum, that means it selects the edge which is a minimum to the already existing vertices in the spanning tree. So now once we select j, we assign j to the set of array, the array T, which consists of set of edges in the spanning tree. So first column is assigned j, second column is assigned near of j, because near of j is 6. So there is going to be an edge between 5 to 6, vertex 5 to vertex 6. Then the minimum cost is incremented with the cost, appended actually, not incremented, appended with the cost of 5 comma 6. And then near of j becomes 0. What is j? 5. So near of j becomes 0. That means we have added that vertex 5 in the spanning tree and created an edge. Then we have another for loop. This for loop is from line 16 to line 19, or line 16 to, let's say, line 18 actually. Line 16 to 18, this for loop is used to update the near array. Update the near array after selecting vertex j and putting it in the spanning tree. So what we did here from line 5 to line 9, same thing is done here. But we only consider the vertices which are not in the spanning tree. Only those vertices near value will be updated depending upon what the cost is, which one is minimum. So depending upon that cost, it will be updated. And finally, min cost is returned. Now remember, whether you try to trace this algorithm or not, or whether you try to work this algorithm, or whether you try to understand, or if you don't understand this algorithm. This algorithm is very important. You by heart this algorithm, because several times this algorithm has been asked in the exam. Now nobody is going to ask you to explain this algorithm. I explained you so that it will be easy for you to remember. and I explained you to show how this works. So this for loop will work for n minus 1 times. All the near values will be updated, and all the vertices will be considered and added to the tree. And finally, it is returned. So this algorithm is very important. You just have to by heart this algorithm, whether you understand or not. Now, let us analyze this algorithm, time complexity. Now, this first statement, that is let KL be an edge of minimum cost in E. The statement is very simple, but what we have to do is we have to sort it, or we have to search the the easiest way is to search all the edges to find the minimum cost edge. Searching edges means if there are E number of edges, then obviously for every edge we need to we need to search. So this statement, first statement, will be taking O of E as a time complexity, where E is the number of edges. Then this for loop will run for n times, where n is the number of vertices. Then the statement within the for loop at line 11, let J, does the same work what the line 3 does, and it takes O of n. Now here we are saying n because n number, we search not the set of edges, we search the near array whether it is equal to 0 or not, depending on that. So let n be the number of vertices, so it takes O of n time. Then this for loop will also take O of n times to execute, so that the near array is updated. And these two, let J be index line 12 and line 16 to 18. These statements are within the for loop. And this for loop itself is running from, iterating from 2 to n minus 1. So it takes O of n. Now, since this statement takes O of n, so ultimately the line 12 statement and line 16 to 18 statements will be taking O of n square and O of n square. So O of n into O of n is O of n square. So this Prim's algorithm, entire algorithm, will be taking O of n square as the time complexity, where n is the number of vertices. So this is what is the Prim's algorithm. Now let us look at another greedy algorithm known as Kruskal's algorithm. And this Kruskal's algorithm works a little different way, and it's very easy to understand the Kruskal algorithm. Here, Kruskal tries to actually arrange the edges, says that the edge, assumes that the edges are arranged according to increasing order of cost, that is non-decreasing order of cost. I said I am writing non-decreasing, that is what is the terminology used in the textbook, but the thing is it is increasing order, so non-decreasing and increasing is same. Now, and each edge, when it's selected depending upon increasing and put it in the spanning tree, it should not create a cycle. That is the basic condition what Kruskal has. That's the basis actually. And the third point is that the edges which are selected so far at any stage should lead to a possibility that a tree will be constructed. Now you're going to understand this, the third point, when we look at how this works. So the Kruskal's algorithm, just the template is same, repeat until, but the thing is here we find minimum edge u comma v, even in Prim's we find minimum edge between two unconnected components. And if this is between two unconnected components, then add that edge to a set A. Here also we maintain a set A which contains the set of edges of spanning tree. Now, until all the vertices was examined. Here in Kruskals, until all edges are considered. So there in Prims, we try to concentrate more on vertices. Obviously, there are also minimum edges selected, but we concentrate on vertices. In Kruskal, we try to concentrate on edges. We make use of edges. Now, let us look at how this Kruskal works. This is very simple compared to Prims. Now, find minimum edge. Now here, remember I told you, it is assumed that all the edges are already sorted into in what do you call increasing order, in ascending order. So, which is the minimum edge? Edge from 1 to 6. Now, how then there is an edge from 3 to 4? Now, initially what happens is the spanning tree T is considered a set of vertices and each as individual tree. So this vertex 1 is an individual tree, vertex 6 is an individual tree, 7 is an individual tree. What this means is all these vertices are without any edges initially. Now there in Prim's algorithm we were taking an edge with 2 vertices and trying to grow the tree in a connected form. But here, what we assume is we already have trees. So as we have 7 vertices, we have 7 trees here. And these trees are disjoint. This is known as actually a forest, a set of trees. Now here spanning tree is nothing but it's a subgraph. So subgraphs, a collection of subgraphs or a collection of trees is known as a forest. So we consider each node as a tree, individual tree, and they do not have any edges. Now what we do is we select the minimum edge. In this case, we have minimum edge between 1 to 6. So we create an edge because this edge is not there in the spanning tree. So we create. So actually what we are creating, we are connecting vertex 6 which was an individual tree and vertex 1 which was individual tree. So now this vertex 1 and vertex 6 becomes a tree. The rest of the others are still trees, disjoint trees, they're not connected. But 1 and 6 is connected. So this becomes, there is an edge connected to the minimum edge. Then that edge is added to A. Next thing is, minimum is, the next minimum edge is 12. This minimum edge 12 is it there, this edge 12 which is from vertex 3 to vertex 4, is this edge there in the spanning tree? No. So add it to the spanning tree. So now vertex 3, a tree 3, tree 4 gets connected with the edge 12. Then what is the next minimum? It is 14. Now this 14 is selected. Is it there? Edge between 2 to 7 in A? No. So connect it and union it with or merge it with or add it or append it to set A. Then what is the next minimum edge? 16 between vertex 2 to vertex 3. Is it there in the tree? No. Connect it and append it in A. Now what is the next minimum edge? Minimum edge is 18. Now 18, if we select 18 and connect it, it's going to create a cycle. So which is not possible. So here in Kruskal algorithm, the statement between two unconnected components, you have to select the minimum edge between two unconnected components. Now the edge from 7 to 4, if we add it, it will be adding an edge, or it will be just like selecting an edge between connected components, but we need to select an edge between two unconnected components. So actually this vertex u and vertex v of that edge, whatever minimum we are selecting, both vertex u and vertex v should be in two different components. Should be in two different components. If u and v are there in the same component means 1 and 6 is one component. 7, 2, 3, 4 is another component. 5 is another component. So they are at this stage three components here. And u and v, if it is in same component, we cannot select that edge. So we have to find minimum edge u and v between two unconnected components. So here 7 and 4 means it is in 7 and 4 both are in same component, so cannot select. So this edge is from 7 to 4 with cost 18 is discarded. That is how we try to avoid cycles. And then the next edge is 22 from 5 to 4. So 5 is in different component, 4 is in different component, so they both are connected. Then the next, and added to set A. Then next is we try to select edge from 5 to 7, which is 24 cost. 5 to 7, 5 is in same component, 7 is the same component. If we select, it creates a cycle. So we don't select this edge, we discard this edge. Then the next edge is minimum is 25 and connects between 6 to 5. 6 is in different components, 5 is in different components, so we join these two. Now, what is the next remaining edge? Is 28. Next remaining edge is 28. If we select 28, it is connecting same component 1 and 2. So this the edge is not selected and it is discarded. Now we have explored all the edges, that is until all the edges are considered, and we have found the minimum cost spanning tree. Now remember, if they are distinct weights, cost of edges, then using Prim's and Kruskal algorithm, we will get the same spanning tree, but with same cost. But if the edges has unique or same weights or cost, then we may get different spanning trees, different minimum cost spanning trees, which actually creates a problem. The cost of this will be 99. Cost of this will be 99. Remember, the same is the cost when we formed the minimum spanning tree using Prim's algorithm. Now let us quickly look at the Kruskal algorithm. Now this is the implemented way or pseudocode of the Kruskal algorithm. We try to make use of heaps here. So we actually, when we make use of heaps, actually what we are trying to do is, we are trying to store the set of edges E in a heap. In a heap, we are trying to store the set of edges. And then this algorithm will make use of disjoint set operations, that is find and union. So line 3 construct a heap of the edges. Line 4 to 5, 4 actually initialize the parent of every vertex as -1, because initially all the vertices are disjoint. So remember the disjoint set operations of union and find. Then we take I as a variable to represent the vertex, and min cost as 0, minimum cost of the minimum spanning tree. We use a while loop from I to n-1. Why I to n-1? Because n-1 will be the number of edges in a spanning tree, and heap not is not empty. Then we delete the minimum cost edge from the heap. That is, each time this while loop runs, we will be picking up the next minimum cost edge. And obviously we have to readjust the heap so that next time when we pick up the minimum cost edge. We find the parent of vertex u and parent of vertex v. And this is done so that we actually try to merge two sets. So if the parents are different of I and j, if parents are same, that what that means is, if parents are same means the edge belongs to vertices which are there in the same component. And if that is true, that means, uh, I mean, it will create a cycle. So if parents are different means there are two different components. So then we assign it into T. This is actually overlapping. You can find this algorithm, I mean, in the textbook. Doesn't matter. It's actually T. If this has overlapped, T I comma 1 is assigned vertex U, and Ti comma 2 is assigned vertex V. So then I is incremented, cost is incremented, and we union both the vertices J and K. So this while loop will run for n minus 1 times or till the heap is empty. Now, if I is not after the while loop terminates, if I is not equal to n, that means they are disjoint. It's not connected, and it will not be a spanning tree, because if the trees are not connected, if the vertices are not connected, then that's not called a spanning tree. So it's will no spanning tree, or we return minimum cost. Now, since we make use of heaps, the uh, to store the elements in the heap and to perform operations of heap, we need E log E times complexity. This while loop will run for n times. Will run for n, actually not n times, E times actually. So this E times, this while loop from 6 to 14 or 15 will run for E times, where E is the set of edges. And each E time we again delete the minimum cost edge and reheapify. Reheapify again will take log E times. So while loop will run for E times, again performing reheapify and all. Other statements are primitive statements. And union operation also, will take O of n. N is nothing but here E itself, edges. So this whole Kruskal algorithm will be taking log O of E log E times. That is, E is nothing but number of edges. So this is how Kruskal algorithm and Prim's algorithm works. Now for your internal, the first internal, you will be having till here. The last topic which is left in the unit 2 is shortest path, single source shortest path, that is Dijkstra's algorithm. I could not cover, though I could have run fast. I mean, taken up fast and covered that, but doesn't make sense. So that we will not have that question. And we will have till minimum cost spanning trees. So this is what we have it. If you have any questions or doubts, just ask me. Otherwise, we can wind up the class. So any questions? Or can we wind up the class? Okay, then it's 11 o'clock. We will wind up this class. We'll meet you after the internals.